This is the lab report for Lab 4. In this video, we analyzed the motion of a weight as it swung across the screen, oscillating. You can see here where we tracked it, and you can also see that the origin was placed at the top point or the base of the spring. We used Tracker to analyze the motion and create data points for both the x and y value, but we did not consider third-dimensional movement to simplify our calculations. We used this lab in order to examine two fundamental principles, one being Newton's second law, which is F equals ma, which can be derived into the equation velocity final equals velocity initial plus the net force divided by mass times t, which you'll see us use later in the Python script. We also use the energy principle, which is about the conservation of energy and based on the systems defined, and we specifically looked at these three energies: kinetic energy, which is from motion; potential gravity energy, which is from distance above the Earth; and the potential of spring energy, which is from the compression or extension of a spring. Here you can see the tracker data that we created by marking all of the x and y values, and they're as a function of time in two separate graphs. You can see here that they have different periods. The period of the x coordinates was 1.636 seconds, whereas the period of the y coordinates was 1.488 seconds. One reason for this difference, of course, might be human error, as we were tracking these numbers by hand and the screens were a bit blurry at some times. Another potential reason for this possible difference could be about forces impacting the y-axis, such as gravity, that don't impact the x-axis, but drag could play a factor in both positions. The initial conditions for the Python code that we created was that the mass of the weight is 0.402 kilograms, the current spring length is 0.7 meters. The initial position is as shown above, which we derived from the tracker data, and the initial velocity was 0, and of course that gravity was acting at 9.8 meters per second squared. We did two calculations, though, to find the spring constant and the relaxed spring length. We found that the spring constant was 5.858 Newton meters, and we found that from the equation T equals 2 pi square root of mass over the spring constant, and arranged the equation to solve for K. We found the relaxed spring length to be 0.0275 meters, which we were able to find by setting Fg, or the force of gravity, equal to the force of the spring, and then using the force of the spring equaling K times L minus LO. As we know everything else now besides the LO, we were able to find LO. In order to make a computer model, we also had to make assumptions. We assumed that we were neglecting air resistance, or that air resistance was not acting upon the object, which can account for the difference between the real and computed position graphs for both the x and the y-axis. Here you can see the most important section of the Python script. This is the iterative loop, and as it iterates through, it becomes more accurate as there's more and more calculations done to keep it up to date and makes it closer to a real-world situation. You can see that in this script, we actually input a data file based on our tracker positions, which is new. You can also see here that it utilizes the energy principle and Newton's second law. Here was the final output from the Python script. You can see the computer model outputted a graph of all of the energies. The main important observations to make are that the total energy remains at 0 throughout, which is represented by the orange line, and that the kinetic, gravitational, spring energies all oscillate back and forth in an even manner. So, what does that graph mean? And more importantly, why is the total energy 0 the whole time? This has to do with conservation of energy, which says that energy cannot be created or destroyed. Since the system includes all of the different energies, such as kinetic, spring, and thermal, and gravitational, the total energy should remain the same, as the system is defined as everything. If we were to narrow the system down, we might actually see changes in the total energy, but due to the definition of the system, the rule of conservation of energy says that the total energy change will remain at 0 the whole time.